Hello, good evening. Okay, good evening. I am Saurav and I welcome all of you to this live session for the NPTEL course, IC Engines and Gas Turbines. This is our third live session. So I think we should begin now. Actually, in this session, we had to change the link for the meeting. So people, if they are using the old link, then probably they are not able to join. But I hope that they have refreshed the page and they have got the new link. But anyways, we will start. Okay. So in previous few sessions, we have discussed the basics of IC engines, various cycles like Otto cycle, diesel cycle, and how to calculate brake, how to calculate BMEP efficiencies, and all these concepts. Okay. So in this session, we will continue our discussion on thermodynamic cycles, and then we will start a discussion on carburation. Okay. So to start with, this is first question, question number 1. It says that in the dual cycle, the heat addition process is characterized by, okay, so you have studied Otto cycle, diesel cycle, and dual cycle, and you know the PV diagrams and TS diagrams, right? So we have to tell that in dual cycle heat addition process, it's which type of process? It is isobaric or heat addition process, that is basically combustion, right? So it is saying that in dual cycle, the entirely constant volume combustion or entirely constant pressure combustion, first constant volume and then constant pressure combustion, and last part says first constant pressure and then constant volume combustion. So you know that in all these cycles, Otto cycle, diesel cycle, and dual cycle, the first of all there is, isentropic compression, and after compression the combustion take place, right? So that combustion in Otto cycle, that is at constant volume. In diesel cycle, combustion or heat addition process that takes place at constant pressure. In dual cycle, they are both constant pressure as well as constant volume, but which one takes place first, constant volume or constant pressure?
Constant volume first and constant pressure.
Yes. So first there will be isentropic compression, then constant volume, this is PV diagram, and then constant pressure, and then isentropic expansion or power stroke, and then exhaust, right? So this is dual cycle. So first constant volume, right? So this is constant volume and this is constant pressure. So first constant volume and then constant pressure. So part C should be the correct option, right? So we will move to the next question, question number 2. For the same compression ratio, which cycle has the highest thermal efficiency? So you have studied the thermal efficiency for all the cycles, for Otto cycle, diesel cycle, and dual cycle. And you have studied that these efficiencies depend on compression ratio, okay, and other parameters. But here it is given that compression ratio is same. For Otto cycle, it is only the function of compression ratio. For diesel cycle, there is one more quantity called cutoff ratio. And in dual cycle, there is one more quantity there called pressure ratio, right? But here it is given that compression ratio is same, then which efficiency, I mean, efficiency for which cycle will be the maximum. To solve this question, I think you can refer a general thumb rule from thermodynamics that for higher efficiency, the mean temperature of heat addition should be more and mean temperature of heat rejection should be less. Okay. If you increase the mean temperature of heat addition, then efficiency will increase. If you decrease the mean temperature of heat rejection, then efficiency will decrease. Okay. So this is one way or one concept using which you can solve this question. Of course, there are other ways as well. For example, you can make the TS diagram, and from the TS diagram, you can have an idea. Okay. But eventually, all the concepts are same. Okay. So this is PP diagram. This is Otto cycle. And if you want to make the diesel cycle, then it will look something like this. From 2 to like this you will get, right? Because you have to keep the compression ratio same. Okay, so if this is V1 and this is V2, then V1 and V2 should be same, or V1 by V2 should be same. Okay, so then you have to compare. So here you can clearly see that in case of Otto cycle, this region, okay, where is the heat addition is taking place? Heat addition is taking place uh, from 2 to 3, right, in Otto cycle. Okay, so the mean temperature for heat addition will be somewhere between T2 to T3. Okay, somewhere between T2 to 3, and in case of diesel it will be between T2 to T3 dash or T3 prime. Okay, and you know that T3 is greater than T3 dash, right? Because if you draw the isotherm, then you can clearly tell, right? Correct. So the mean temperature of heat addition in case of Otto cycle is greater than the mean temperature of heat addition of diesel, right? And all other, other process are same. Okay, compression ratio is same and heat rejection process is same. So efficiency for same compression ratio, this implies for same compression ratio, efficiency of the Otto cycle is greater than efficiency of DL cycle. Okay, and dual cycle is in between. Okay, dual cycle is in between these two cycles. Okay, other way is using the TS diagram. If you make the TS diagram, then 1 to 2, so 1 to 2 it is constant process, sorry, constant isentropic process. And if you let us say if you want to make it for Otto cycle, then 2 to 3 will be a constant pressure process. Okay, so let us say it is constant pressure. Okay, then 3 to 4 it is isentropic. Okay, sorry, 1 to 2 this is isentropic. 2 to 3 it is constant pressure, and 3 to 4 again it is isentropic, and 4 to 1 again it is constant pressure. Okay, and for diesel cycle it will be constant volume. So constant volume lines will be little below this line. Okay, so this is 3 dash. So here also you can see that heat rejection is same in both cycles. Okay, so this part just below, so this part is heat rejection, right? This yellow line, it is the yellow part, it is heat rejection. So this is Q out. Okay, sorry, work output divided by heat input, and work output is basically heat input minus heat rejected divided by heat input, and this will be like Q out minus Q in neta. Okay, so Q out is same for both these cycles, right? The yellow part you can see here, the yellow part you can see here, it is same for both, right? So Q out, this term is same. The only term that is different is Q in. Okay, so for Otto cycle, the Q in will be this region, right? 2 to 3. And for diesel cycle, it will be 2 to 3 dash. Okay, so you can see that area under curve 2 to 3 dash, it is smaller as compared to area under curve 2 to 3, right?
Yes, sir.
So area under 2 to 3, it is greater than area under 2 to 3 dash. So this means, sorry, so this means Q in for Otto cycle, it is more than Q in than diesel. Diesel. Okay, and Q out, it is same. So from this concept also you can tell that for same compression ratio, efficiency of Otto cycle is greater than efficiency of diesel cycle. Okay, but if you don't want to do this analysis, you just try to make a estimate of the mean temperature of heat addition and mean temperature of heat rejection. Okay, so if the mean temperature of heat addition is more, that mean the efficiency will be more, and if the mean temperature of heat rejection is less, that also will result in more efficiency. Okay, so I hope this is clear, and we can move to the next question. Okay, is there any doubt in the previous question? If no doubt, then we can proceed.
No, sir.
Question number 3 says, in the TS diagram comparison of Otto diesel and dual cycle, the same compression ratio, okay, the same previous one. The heat rejection area Q out is, so we have already discussed, right? TS diagram, we can make it again. 1 to 2, 2 to 3, this is for auto, this is for diesel. I'm not making for dual, you can make it, otherwise this will be look, very messy. Okay, so the heat rejection, it is from 4 to 1, right? Heat rejection is 4 to 1, and that is same, correct? So that is common. So this part is common. So answer will be same, right? Same for all cycles, correct? So part C should be the correct option. And in question number 2, which cycle has the highest thermal efficiency for the same compression ratio? Answer is Otto cycle. Okay. Heat rejection is same, but heat addition is different. So for which cycle heat addition is maximum?
Auto cycle.
Otto cycle. Okay. Question number 4. When comparing cycles based on the same peak pressure instead of same compression ratio, which cycle would likely have the highest efficiency? So in the previous questions, the compression ratio was same. Now compression ratio is different. Peak pressure is same. Okay. So now we have to tell that which cycle is likely to have the highest efficiency. Otto cycle, diesel cycle, dual cycle, or cannot be determined. Again, if you try to use the same rule of thumb, that mean based on the mean temperature of heat addition and mean temperature of heat rejection, then you can answer this question easily. We have to keep the peak pressure same, right? So for which cycle the efficiency will be greater, maximum?
Diesel cycle.
Yes, diesel cycle. Because heat rejection is same, right? Heat rejection is same. The only thing that is changing, that is heat input. Okay. Diesel cycle. TS diagram also you can make and check. right? Same peak pressure, heat of diesel, that is highest, then dual, and Otto cycle has the minimum efficiency, right? So engines usually, if you want to compare the engines, then instead of comparing the compressor ratio, it is better to compare on the basis of peak pressures, right? Because if you want to compare the diesel engine and petrol engine, then definitely they will have different compression ratio, right? Because diesel engines are designed to work on higher compression ratio so that their fuel can be ignited easily, right? And in Otto cycle, that is basically for petrol engine or gasoline engines, they are designed for relatively lower compression ratio, because in those type of engines you are using spark plug. Okay, so definitely the compression ratio is different. So instead of compression ratio, if you are using peak pressure for comparing their efficiency, then it is more realistic point of view. Okay, so in most of the cases, efficiency of the diesel engine is greater than efficiency of petrol engines, right? Because compression ratio is, very different. In uh, petrol engines, compression ratio will be of the order of like 7, 8, 9, 10, or 12, like that. In diesel engines it will be like 16, 17, 18, okay, in that range. But peak pressure, if you want to compare, then if you are assuming that peak pressure are same, then it is more realistic. Okay, of course peak pressure in diesel engine will be greater than the peak pressure in Otto cycle, but for comparison purpose it is a better comparison. Okay, I hope this is clear, and we can move to the next question. Question number 5, it is saying that the mathematical expression for the efficiency of dual cycle depends on. So you have to tell the efficiency of dual cycle. If you know the formula, then you can easily tell, but we have already discussed, right? We have discussed in the first question itself that the efficiency of Otto cycle depends only on compression ratio. For diesel cycle, it depends on compression ratio and cutoff ratio. And for dual cycle, it depends on three things: compression ratio and cutoff ratio and pressure ratio. Okay. So efficiency for Otto cycle, it depends on only on compression ratio. Okay. For diesel cycle, it depends on compression ratio and cutoff ratio. And in dual cycle, it depends on compression ratio, cutoff ratio, as well as pressure ratio. Okay, correct? Right? If you want to write the mathematical expression, it is 1 divided by 1 1 minus 1 divided by k2 minus 1. Here there will be cutoff ratio, something that will depend on cutoff ratio, and something that will depend on pressure ratio. Okay,
Yes, sir.
so it is the function of all these three quantities. So part B should be the correct option. Okay, so these were MCQs, and now we have some numerical problems. Okay, so let's try to solve. Question number 6. It says that a four-cylinder, four-stroke spark ignition engine has a displacement volume of 300 cc. So we have discussed what is displacement volume, right? Displacement volume or swept volume, both are the same things per cylinder. Okay, so it is four-cylinder engine. It is a four-cylinder engine, and per cylinder the displacement volume is 300 cc. So the total displacement volume will be 300 cc times 4. Okay, so 1200 cc. The compression ratio of the engine is 10 and operates at a speed of 3000 revolutions per minute. The engine is required to develop a output of 40 kilowatt at this speed. Okay, so this is this information is given, and we have to find the cycle efficiency, the necessary rate of heat addition, the mean effective pressure, and the maximum temperature of the cycle. And we can assume that the engine operates on the Otto cycle. It is already given that, okay, it is spark ignition engine, and we can assume that it operates on Otto cycle. Why we are assuming Otto cycle? You can ask that it is spark ignition engine, so it will have to operate on Otto cycle. So is it like that? No, because
Yes,
the
sir.
actual, no, it is not like that, because the actual cycle, it is very different from uh, the Otto cycle. These Otto cycle, diesel cycles, these are ideal cycles, and the actual cycles, they are very different from the ideal cycles. Okay, so that's why we are assuming that engine is running on Otto cycle, but in reality this will not be the Otto cycle. Okay, because in all the cycles you have studied, that is, cycles are basically cycles, right? And all the processes, they are reversible processes, right? And the reversible processes, they are quasi-static processes. They takes place at very slow process. Okay, infinitesimally slow, right? So all
Yes.
the all the times they are in equilibrium, thermodynamic equilibrium. But in real case, do you think that it is happening at very slow rate? No, it is happening at very fast rate, right? It is given that it is rotating 3000 times per minute, right? So nothing is in equilibrium. And on the top of that, it is not even cycle. Whatever charge you are sending in the next cycle, you are getting the different composition. Okay, so diesel cycle or Otto cycle or whatever cycle, these are ideal cycles. So that's why it is written that we have to assume that it is Otto cycle, but in reality it is different. Okay, so maybe I can show you the real cycle. I think I have already shown, but I will try to show you some real data, uh, and then it will be better if you can compare it from the real cycles. But today I don't have, but I will try to show you in the next session. Okay, so please attend the next session, and we will see the real data. Okay, but anyways, for the time being, let's focus on this question. So we can assume that engine runs on the Otto cycle. The pressure and temperature at the inlet conditions are 1 bar and 27 degrees Celsius. Okay, fine. And one more part is there. So operating a diesel cycle. Okay, so cycle will be changed so that we can compare the efficiency of both Otto cycle and diesel cycle. But let's start with the first part. Displacement volume per cylinder, it is given 300 cc. Okay, displacement volume per cylinder, it is 300 cc. Compression ratio is also given, right? Hello, compression ratio is
Yes,
also
sir.
given. Compression ratio is given, it is 10, right? And rpm, it is 3000 rpm, and power output is 40 kilowatt. Okay, so we have to find what cycle efficiency. So for cycle efficiency, it is given that we can assume it is Otto cycle. So for Otto cycle, we can use the direct formula. So for Otto cycle, it is n is equal to 1 minus 1 divided by compression ratio to the power gamma minus 1, right? Correct? So compression ratio, it is given to be 10 to the power gamma, uh, yes, gamma is 1.4, right? 1.4 minus 1. So you can quickly calculate this value. 1 minus 1 divided by 1 minus
0.3981.
0 point.
3981.
So it is very less. I think it should be a little more. So let us try to do it. 10 to the power 0.4. It is 6, 0.6. Okay, 0.6019. Okay, so efficiency is 60 point, around 60%. Okay, so this efficiency is very high. In reality, the efficiency will be like 30%, 40% in that range. Okay, because you are using the auto cycle assumption, and that is ideal, ideal cycle. So in ideal cases, you get very high values of efficiencies. Okay, so efficiency we got. Another, what else we have to find? The necessary rate of heat addition. So for heat addition, what will be the heat addition? Rate of heat addition actually. Okay, so the definition of efficiency, it is rate of work output or power produced divided by rate of heat input, right? So efficiency you have already got, it is 0.602, and power that is required to be developed, this is 40 kilowatt, right? It is given in the question, 40 kilowatt, right? So 40 kilowatt divided by the rate of heat input. So from here you can find rate of heat input. This will come out to be 40 kilowatt divided by 0.602. Okay. So it is around 66.45 kilowatt. Okay. So this is the rate of heat input, and heat addition we got mean effective pressure. So how do we calculate the mean effective pressure? We have discussed the definition of mean effective pressure in the previous sessions, right?
Network upon swept volume.
Network upon
Swept volume.
swept volume per cycle, right? Network per cycle. Okay, right?
Yes, sir.
Okay, so network per cycle. So this will be mean effective pressure. So work output per minute, sorry, per second, it is given, right? It is given for per unit time. So that is basically power, right? So net work per unit time, this is 40 kilowatt. But for one cycle, we have to find this, right? So we have to find in one unit time, or in In 1 unit time or 1 second, uh, how many cycles will be there, right? Or per cycle, how much work will be produced, right? So it is rotating at 3000
1000 RPM.
revolutions per minute. And it is given that it is a which type of engine, 2-stroke or 4-stroke? 4-stroke, right? So when in case of 4-stroke engines, how many cycles are there in one revolution? One revolution of crankshaft, how many cycles are there?
15,000. Oh, 1500.
Yes, so in one revolution there is half cycle. Okay, so for one cycle there should be 2 revolutions, correct? Right, right. So for 4-stroke engine there will be 500 cycles per minute, correct? Right. So this is per minute, and if you want to convert this thing to per second, you just divide it by 60, right? So 500 divided by 60 cycles per second, right? These many cycles per second, right? So in 1 second,
25 cycle per second.
okay. So in 1 second, these many cycles are there, whatever the value is, no problem. So in 1 second, how much work is produced? 40 kilojoule, right? And in 1 second, there are these many cycles, right? So in one cycle, how much work will be produced? So it will be 40 kilojoule divided by this quantity, right?
Yes.
Correct. So if we find this value, 40 divided by 1500 divided by 60, then we are getting
1.6.
1.6 kilojoule per cycle. So work per cycle we have got, right? So what was the definition? Definition was net work per cycle divided by swept volume, right? Net divided by swept volume. So what is the swept volume? And one more thing, this power is generated by 4 cylinders, right? Correct. This is generated by 4 cylinders. We have to tell per cylinder. Okay. So we have to tell net work output per cycle per cylinder, right? Correct. So then again we'll have to divide this quantity by 4 because there are 4 cylinders. It is a 4-cylinder engine, right? So we get 0.4 kilojoule per cycle per cylinder, right?
We can calculate it.
Hmm? So mean effective pressure will be 0.4 divided by swept volume. Where is the swept volume? It is 300 cc, right? 300 cc. So cc means cubic centimeters and it is kilojoule per cycle or per cylinder, whatever. And if you want to write it in meter cube, that is the SI unit, then in 1 meter cube, how many cc are there? Hello?
Hello.
In 1 meter cube, how many cc are there? Am I audible? Hello? Hello? Hello?
10 to the power 6.
10 to the power 6. So 10 to the power 6 meter cube. Okay. So what will be this value? PM? Hello? There will be one minus, right? We are converting cc to meter cube. So in 1 cc, there will be 10 to the power minus 6 cc. Okay. Anyways, so if you calculate this values, you will find that this comes out to be 400 divided by 300, and there is 10 to the power minus 6. So it will be 13.3 into 10 to the power 5
Hello,
Pascal.
sir.
Huh.
300. What is a 300? There.
Hmm? 300, this swept volume. The definition of mean effective pressure is net work per cycle divided by swept volume. So net work per cycle you have got, right? So net work per cycle is 0.4 kilojoule per cycle per cylinder, right? So this is 0.4. Then you have to divide by the swept volume. So this is the swept volume, 300 cc. And from
Sir,
cc you have
my question.
swept volume, displacement volume per cylinder.
Given my question.
Yes, it is a given question.
Yes.
It is given where it is. Yes, here it is. Can you see it? Here?
Yes, sir. Yes. Yes.
Okay, so we have got mean effective pressure as well. Now we have to find the maximum temperature. Okay, so at what point the temperature will be highest? So at what point temperature is the highest? After the compression stroke or after the heat addition process or after the expansion process? So after which process temperature is maximum?
Heat addition.
Heat addition, right?
Yes.
This is Otto cycle. So 1 to 2 it is compression, then 2 to 3 it is heat addition, and 3 to 4 it is expansion. So we have to find the temperature at point 3, right? So here temperature will be maximum, right? T max is basically T3. We have to find T3. So now see, let us see what we have. Do we have which temperature we have? We have inlet temperature, right? T1 we already have. So from T1 we can calculate T2, and from T2 we can calculate T3. Okay, so first of all let us calculate T2. So 1 to 2, which type of process is this? This is adiabatic or asentropic process, right? So you can use P1 V1 to the power gamma is equal to P2 V to the power gamma, or in terms of temperature you can write you can use the ideal gas equation PV is equal to nRT, right? So you can write T1 V1 to the power gamma minus 1 is equal to T2 V2 gamma minus 1, correct? So T2 will be equal to T1 divided by V1 by V2 to the power gamma minus 1, right? Correct? T1 it is given in the question. So how much is T1? T1 here it is given that it is 27 degrees Celsius, right? Correct? So T1 it is 27 degrees Celsius. Then you will have to convert this thing in Kelvin. 27 plus 273 Kelvin or 300 Kelvin. So T2 comes out to be 300 Kelvin times V1 by V2. What is V1 by V2? This is compression ratio, right? Compression ratio is given. It is 10 to the power gamma minus 1. So 1.4 minus 1. So you have to calculate this value. 300 times 10 to the power 0.4. This comes out to be 753.56 Kelvin. Okay, T2. So now we have T2. So from T2 we can find T3, right? So T2 to T, 2 to 3, which type of process is this? This is heat addition process. Heat addition process, right? And how much heat is added from 2 to 3? This will be mCV because it is constant volume process into T3 minus T2,
T2.
right? So T3 minus T2 will be equal to heat added divided by mCV. So CV it is, I think, given in the question. Only thing is that we need to find M, right?
Yes.
We have to find M. So how do we find M? CV it is given. Okay, CV it is given. And Q in, it is, this thing is also given, right? This is also given. Correct? Right?
Yes, sir.
Okay. So, but this heat addition is for, per unit time. We have to find heat supplied per cylinder per cycle, right? We have to find heat supplied per cylinder per cycle. So I think this we have found out already. Q in, this was 66.5 kilojoule. So heat supplied per cylinder per cycle will be how much? 66 kilowatt, and there are 4 cylinders, right? And how many cycles in 1 second? 3000 cycles, 3000 revolutions in 1 minute. So there will be 1500 cycles in 1 minute, and there will be
5
50.
cycle per second.
Okay, so this will come out to be 25, right? Like this. So 66.5 divided by 4 into 25, correct? kilojoule per second, right? So this will come out to be 0.665 kilojoule. सेकंड तो चला गया यहाँ से, it was kilowatt, kilojoule. So this is heat supplied per cylinder per cycle, right? Correct, right?
Yes, sir.
So Q2 to 3 is mCV T3 minus T2. This we have already discussed, right? Now we have to find CV, it is given, T2 we have, T3 we have to find, Q we have got. Now only thing left is M, right? We have to find M. So to find M, you can use ideal gas equation, right? So
Yes.
ideal gas equation, let us apply ideal gas equation at point 1. Ideal gas equation at 1. So it will be P1 V1 is equal to R T1. So V1 will come out to be R T1 divided by P1. So R, it is 287 multiplied by T1, it was 300 Kelvin, actually it was 27 degrees Celsius, and P1 it is given to be 1 bar, right? So 1 bar means 1 into 10 to the power 5 pascals, right? So V1, this is a specific volume actually. So this is 0.8 to 87 multiplied by 300. So 86 something.
861 meter cube.
Right. So 0.861 meter cube per kg. Just a second. Okay. So we have this. Okay. So we have a specific volume. What we have? A specific volume. So specific volume is basically volume per kilogram. But we need what? We need kilogram. How many kilograms we have? Right? So mass will be equal to total volume multiplied by specific volume. So we have to find the total volume, right?
Yes.
So for total volume, what can we do? It is given that it is 300 cc. Okay, displacement volume is given, right? So the total volume will be what? Displacement volume plus clearance volume, right?
Yes, sir. Total volume.
Yes, sir.
So V1 will be displacement volume plus clearance volume, right? And if you take VD common, displacement volume common, then it will be VD divided plus VC by VD. And VC by VD, this is just
Clearance.
reciprocal of your compression ratio, right? Correct?
Yes. Yes, sir.
1 by 10. So V1, it will come out to be displacement volume is how much? 300 cc plus 1 divided by 10. So it will be 300 cc times 1.1, right? So it will be 333, right? Into 10 to the power minus 6 meter cube. I have converted cc into meter cube. right? So now you can 3
330.
okay. And
Clear, sir.
okay, so the mass will be volume divided by this thing. So 330 divided by hello.
Yes, sir.
Hello.
Mm-hmm. Hello.
Hello.
Yes. Am I audible?
Yes, sir. Audible.
Okay. So what will be the volume now? Sorry, mass divided by 0.861.
861. 383.275.
Whatever units. Okay. I'm not
10 to the minus 6.
कितना आया? 0 point
Sir, 3.83 into 10 to the minus 4
3.83
into 10 to the minus 4
into
kg.
10 to the power minus 4 kg. Okay. So I'm assuming that this value is correct. Okay. So now we have got the mass. So where we needed mass, here we needed mass, right?
Yes, sir.
So क्या था? Q223 is equal to mCV T3 minus T2, right? So now we need T3 minus T2. It will be equal to Q223 divided by mCV, right? And Q223, this we have already got, and this what 0.6 something, I forgot. 0.665 per cylinder per cycle, right? 0.665 divided by mass, we have got 3.83 into 10 to the power minus 4 kilogram divided by CV. It was given in the question
0.718.
0.717
No.
kilojoule per kg.
No.
Okay, so 717
2.42.
7. So how much?
Sir, 0.717, it in a kilojoule per kg Kelvin. So can we convert into joule per kg Kelvin, or simply?
Let us take all the units in SI units. So first of all, let us check the unit of Q. So Q, which unit it is there? So it is kilojoule. Okay, so
Then
it is multiplied by 10 to the power 3. So now it is in joule. Okay, and 717, this is also in kilojoule. So again we need to multiply by 3, 10 to the power 3. So these stuff will cancel out. Now we will get the SI unit of temperature. So that will be Kelvin. Okay.
Yes, sir. 3. 2421.60. 21.60.
Okay, let us just cross check. 0.665 divided by 3.83 into 10 to the power
minus 4.
minus 4
Into 0.
into 0.717
Into 10 to the 3.
ना वो तो कैंसिल हो गया ना 10⁻³
हाँ
यहाँ पे कुछ ब्रैकेट का चक्कर हो गया। Okay, so yes, 2421 Kelvin.
0.60.
Okay, just up to one place is fine.
Oh.
So we
So
have
this
got
is
all the values. We have got the maximum. Okay, no, sorry. So this is
That-
T3 minus T2. This is not the maximum pressure, maximum temperature. Maximum pressure will be T3 is equal to T2 plus this value 2421 Kelvin. And T2 was, how much was T2? T2 was 753. 753. 753 plus 2421. This much Kelvin.
3174.
3
174.
3174 Kelvin. Okay,
This is
so this
large
is the
temperature,
Hmm?
very high, very high
Yes,
temperature.
yes, this is very high temperature. So after combustion, temperature ranges are like these. Okay,
Yes, sir.
and also we are assuming that this is ideal cycle, and in
Oh.
ideal cycles, values are usually high. So, but temperature ranges are like in this range. Okay,
Yes, sir.
so these calculations we have done by assuming that cycle was Otto cycle.
Up to second.
And second part says that if the above engine is a compression ignition engine, okay,
Oh.
operating on diesel cycle and receiving heat at same rate, we have to find the efficiency, maximum temperature of the cycle, cycle efficiency, power output, and the mean effective pressure. So same thing we have to do, assuming that this is diesel cycle. Okay, so should I do it or you will do it by yourself?
Yes, sir. We will do.
So if you want to take the screenshot or you want to note it down, then you can note it down. Or if you want me to solve, then I can solve. Or maybe I can just tell the answers
Hints.
from where I have taken this. So
Sir, you just write
yes,
hints.
I just write the
Hints.
hints are same. Okay, so whatever steps you have followed, the same steps will be there, but the only extra thing will be the cutoff ratio. Okay, and you know how to find the cutoff ratio,
Cutoff ratio. Yes, sir.
right? So that process is which process? That will be constant pressure process, right?
Oh.
Okay.
Yes.
Yes, sir.
So that is only difference. In Otto cycle, there the heat addition takes place at constant volume. In diesel cycle, that will be a constant pressure. So that is the only difference. And other things we have to assume that they are same, right?
Yes, sir. We'll
Heat
do.
addition, yes. So I can write the answer and you can just compare them later.
Oh.
Okay. So
Sir, this video upload in website na? After this Zoom.
yes, maybe tomorrow I can upload because
sir.
it takes some time to processing. So when you go to your NPTEL page, there is something, some tab. I think. Let me check
Yes,
what.
sir. Yes, sir. Last time you uploaded, I saw.
Yes. So there is problem solving session, and when you click problem solving session, there is.
Bottom part.
I think you get some Google Sheet. In those Google Sheet, there are links.
Yes, sir. Sir, I have some doubts, sir. In last assignment 2, one question was asked in four-stroke SI engine, maximum pressure given 200 bar and minimum pressure given 5 bar and compression ratio given 8. Then to find the mean effective pressure, how to solve that? Basically, mean
Okay.
effective pressure equal to what done per stroke volume. Here data are a little.
Just let us write the answer of this question, and we will refer to that. Okay.
Yes, sir.
I will just quickly write the answer of this question, and then we will move to that. So T3, this is given to be 2192 degrees Celsius. Okay. Efficiency, it is coming out to be 46.7%. And mean effective pressure, this is coming out to be 10.35 into 10 to the power 5 pascals. Okay, so these are the values. So maybe in your calculation you can get little different, maybe some percentage different, but order will be the same. And you will, the important that is to be noted here is that efficiency for the diesel will be more or less. It will be higher or greater.
Higher, sir. For same compression ratio or different compression ratio, sir?
So here, what is given in the question? Compression ratio of 10. Compression ratio is 10. It is already, I mean, in the beginning itself, it is given the
Then
compression ratio of 10.
diesel is lesser efficient than auto cycle.
Efficiency of auto cycle will be
Greater.
more, right? So auto cycle, what efficiency you got? We got 60% efficiency. In diesel engine, answer whatever I have. So it is given 46 point something. So this is less. So this seems okay. Okay. So method is same, only just the process of heat addition is changed from constant volume to constant pressure. Okay. So I think you can easily do that. I had one more question in which the peak pressure was same, but again, so method is same, right? Just to give you an illustration that yes, for the given compression ratio, auto cycles are more efficient, and for given peak pressure, diesel cycle is more efficient. Okay. So what problem you had in session 2? Where it is? Do you remember question number?
Question number, sir?
No, you had some problem in last session.
Yes, sir. Assignment 2.
No, it is not assignment. These are, I mean, I cannot tell you the assignment problem answers. So
No, sir,
these are,
it is already done, sir. It is already done. 1 and 2.
it is uploaded.
Already done, sir, and evaluated already.
Okay, then I need to check the assignments. So for currently, I don't have that. So maybe I will
From
go through the
assignment.
assignment and we will solve in the next session, maybe. Okay.
Yes, sir.
I will have to log in and check the questions.
Yes,
So
sir.
I will just note it down. And so which problem you are having problem?
Um,
Hello? Maybe I should quickly check that. Week 2.
Assignment 2, I
Just
think, sir.
just give me 1 second. खुल नहीं रहा है. क्वेश्चन नंबर क्या है? क्वेश्चन नंबर असाइनमेंट 2 क्वेश्चन नंबर.
Question number, I need to check, sir.
So what was the problem? If you just tell, then maybe I can check.
Sir, maximum pressure given 200 bar, minimum pressure given 5 bar, compression ratio given 8, four-stroke SI engine is simply told. Then find out the mean effective pressure.
Okay, I think you can find that question number 9. It is question number 9, right? I will copy and let us see if I can paste here.
Yes, sir. Question number 9.
ये क्वेश्चन है ना?
Yes, sir.
Okay. For this is assignment 2. For a 4-stroke SI engine, the maximum and minimum pressure inside the cylinder during each working cycle is 200 bar and 500 bar respectively. If the compression ratio of engine is 8, then we have to find the mean effective pressure. Right? So this is which cycle? SI engine. So for SI engine, you can assume that this is an Otto cycle, right? So for Otto cycle, you just make the PV diagram. So 1 to 2, it is isentropic compression. Then 2 to 3, it is constant volume heat addition, and 3 to 4 again isentropic, and 4 to 1 it is constant volume, right? So it is given that maximum and minimum pressure. So minimum pressure will be at which point? It is at 0.1, right? So P1 it is 5 bar. So P1 it is 5 bar, and P2 it is 200 bar, right?
P3.
Sorry,
P3.
P3 it is 200 bar, and compression ratio it is V1 by V2 it is 8. So what we have to find?
Mean effective pressure. What done for stroke volume?
Mean effective pressure. So what will be the mean effective pressure?
What done per cycle divided by stroke volume or displacement volume?
Right. Work done divided by displacement volume. So where is the work done?
Efficiency into heat addition.
But where is the heat addition?
Yes, sir. That's a loophole, sir. That's why I unable to solve.
With the given data, you can find the values. So work done during power stroke. Can you do now? Hello?
Yes, sir.
Can you do now?
How to do, sir? CV T4 T3 minus T4. CV T4 CV T3 minus T4.
Don't go on temperatures. Just use those work done formula. P1 V1 minus P2 V2 divided by gamma minus 1 or 1 minus gamma. Those type of formulas.
Achha, then P3 V3 minus P4 P4 by gamma minus 1. P3 V3 minus P4 P4 by gamma minus 1.
Yes, something like that.
Then P3 by P4. V3
But with the given data, you can find the answer. But I have some, more problems on carburetor as well. I think we should quickly solve those as well.
Sir.
Otherwise, they will be left, and we will come back. Okay.
Yes, sir.
Okay. So venturi in the carburetor results in. So you know how the carburetor works. Just a quick overview that it works on the venturi principle. So in venturi principle, you have one pipe. So at some point in that pipe, you have little less, cross-sectional area. So in that cross-sectional area, the velocity of air is more and pressure is less as compared to atmospheric pressure. And there is one chamber in which fuel is there, and the pressure in this chamber is 1 atmosphere pressure, and it is connected using some pipe to this region. Some thin nozzle is there. Since pressure at this point is dropped, it is lesser as compared to atmospheric pressure, so fuel comes from this chamber to your venturi tube. So this is the governing principle. Okay. Yes. So venturi in the carburetor results in
decrease of air velocity.
Decrease of air velocity, no.
Increase, sir, because throughout
Because the cross-sectional area is reduced, right? So increase
Yes.
in air velocity, increase in air velocity, and reduction in decrease in pressure, right?
Yes.
Question number 8. Choke is closed when the engine is. So you have the idea how this carburetor work, or should I explain it?
Cold.
Yes, choke is closed when the engine is cold. Yes. So many times whenever you are starting your bike, and sometimes it does not start easily. So there is one switch that you call choke, right, on your handle. Then you press that button, choke button, and then your bikes get started, right? Have you experienced this?
Yes. Yes, sir.
Yes,
बोलते
sir.
ना चोक चोक ले लो, तब वो स्टार्ट हो जाती है. So what this choke actually is doing? So you have idea, or should I explain the working? Because correct answer you already told.
Explains.
Okay, so the purpose of choke is to provide more fuel. So how it is happening? Just I will make a rough diagram, not very good diagram, but anyways. Okay, so this is your venturi. This is your throttle valve. Okay, so this is your throttle valve. This can rotate. For example, this currently this is closed. Okay, and when it is open, it will be like this. Okay, and similar thing is there that is called choke. Okay, so let us say it is opened. Okay, and here you have nozzle which is connected to a fuel reservoir, and in the fuel reservoir there is some floating mechanism which will provide the fuel. So this floating mechanism, have you seen it? You can see this in your plus, okay, in your washroom.
Yes, sir.
Yes, when you do plus,
Water
all the
tank.
waters, yes, when you do plus, the waters comes out, and when the tank is empty, again that tank fills out to a particular level. So that mechanism is governed by this, you know, floating thing. Okay, so when the water goes down, so this ball, this also comes down, and your opening, so that was closed, now this open when this balls come down. So water comes in. Okay, so it start filling in. Okay, so when the level reaches to a certain level, then this ball moves with the level, and this this passage get closed. Okay, so this is the basic mechanism. You can see some animation, then it will be more clear. Anyway, so the basic purpose of this floating system is to maintain a level in this reservoir. Okay, and when and the pressure at this reservoir, this is 1 atmospheric pressure, and pressure in this this region, this is less than atmospheric pressure, right? Less than 1 atm. Since pressure is less, so this petrol or gasoline, this comes from this reservoir to this area, and since the opening at this pipe, it is very small. So when the opening is very small, so this comes out some sort of spray or like that, right? When the opening is very small, you get some sort of spray, right?
Yes, sir.
So your fuel droplets will come here, and it will get mixed with the air, and you will get a homogeneous mixture. Okay, so this is the working principle. And one more thing is there. And why this air is coming in? Why this air is coming in? Because this is connected to your cylinder, right? This is your connected to your cylinder. So this is your cylinder piston. So when the piston goes down, right? When the piston goes down, then vacuum type of thing is created. So it sucks the air in, right? Correct? Hello?
Yes, sir.
होली में पिचकारी आती थी ना पहले, पानी कैसे भरते थे उसको, ऐसे पिस्टन अपन खींचते थे बाहर, तो पानी भर जाता था.
Yes.
So same thing is there. So piston is going down, so it is sucking the air in, so air is coming here. So now you can control the flow of air using this throttle valve. Okay, this is throttle. Okay, if you close the throttle, the less air will come, right? And the less air will come, so the less fuel air mixture will come in, right? So depending on how much air is coming in, so in that proportion, this fuel will get mixed with the air, right? So more air coming in, more fuel air mixture you will get. Less air coming in, less fuel air mixture you will get, right? But if you want to get more fuel, then what you can do is you just close uh, this choke. Okay, now if you have closed this choke, so what will happen in this whole area? Some sort of vacuum will be created, right? Here at this point pressure was already less. Now you have also closed the choke valve, so pressure will drop even more, correct?
Yes, sir.
ये चोक पूरी तरह से बंद नहीं करेगा. Some part will still be open so that air can come in, but some part it will block so that at this point more pressure drop will be there, right?
Yes.
Because it is creating some sort of vacuum type of thing. So now there is more pressure drop, so now more fuel will come inside, right? Are you getting?
Yes,
So
sir.
now you get more fuel. So that is what choke is doing. When you have closed the choke valve, so you are getting rich mixture. Okay, so in the mixture there is air and fuel, and you try to maintain the stoichiometric ratio. Okay, somewhere near that in that range. Okay, but sometimes when the bike does not start, especially in the cold conditions, so during starting, when you starting your bike, then you need little more fuel. Okay, so you just close the choke valve and more fuel comes in, and when your bike get started, you just open the choke valve and your bike will run normally. Okay, so
Yes,
choke
sir.
valve basically it is preparing a rich mixture. It is putting more fuel in the mixture, and you are getting a rich mixture so that you can start your bike or your engine easily. So this is what is done by a choke valve. Okay, and throttle valve it controls the amount of mixture. So I will suggest that you go through some animations. So they are very beautiful animations. So how these parts are moving and what are different types of carburetors. In fact, there are transparent carburetors. For example, in my lab, one of my colleague, they have transparent this carburetor. They can see how this spray is coming, how this is getting mixed with the air. So people are doing different things just for your to get better insight what is going on. So all those videos are available publicly, so you can go through them. Okay,
Sir, how many type of carburetor?
in our lectures we have discussed only this float type of carburetor, but there are different carburetor for different purposes. Okay, and this is the simplest one that we have described, and it will prepare a depending on this design, it will prepare a fixed type of mixture. Okay, but in real case you need different type of mixtures for different driving conditions. For example, when you are idling, when your pressure sorry, when your load is very less, then you need rich mixture. When you are cruising, then you need somewhere near stoichiometric mixture. When you are accelerating or you are having more load, then again you need rich mixture, right? So depending on
Yes.
your running condition, you need different type of mixtures, but this simple mechanism cannot provide all those type of mixture. So there are a lot of modification in this simple design. Okay, so a purpose of modern carburetor, okay, good carburetor is that it can prepare all type of mixture that is required for different running conditions. Okay, but the
Okay, sir.
basic concept is same. For example, for idling you can add just one more pipe, right? You can add one more pipe, and you just close the throttle. Okay, you just close the throttle, and now air will come from this pipe, and again this pipe can be connected with this uh, fuel tank or fuel chamber of the carburetor, and you will get a mixture but not that much rich. Okay, less fuel will come in, right? You need some fuel, otherwise your bike or your engine will get, it will not it will get stopped. You don't want to stop your engine, but also there is no load. Okay, load is very less, so you need less fuel but you need some fuel. Okay, so for that you can use another pipe. So this is one modification. So there are
Lean
a
fuel.
lot of modifications.
Lean fuel.
Yes, you need if you need lean fuel, you can use these type of arrangements. And when you reach fuel, then you close the choke valve, and so lot of modifications are there. So this is the simplest one. Anyways, I think answer you have already got. The choke valve is closed when the engine is cold. So once engine is started, it is no more cold, and you can just open your choke valve. Okay. Okay, so if it is clear, then we can move to the question number 9. During the starting, petrol engine requires,
Rich fuel.
yes, rich fuel. So there was some diagram, I think you might have seen on this. This was throttle requirement, right? And here it was
Total of versus fuel air ratio.
fuel air ratio, and it was something like this, right?
Yes, sir.
Butter curve.
5% to 20%, then 20 to 80%,
80 to
and so on.
100%.
Right? So this was cruising, right? This was idling. This was acceleration, or high load. So during idling or starting, you need rich mixture. Okay, so if it is clear, then we will move to question number 10. So
Sir,
stoichiometric.
Sir, one question. A simple carburetor supply rich mixture during. So option में starting, idling, cruising and acceleration. तो first कौन choose करेंगे?
Idling maximum power.
I did not get your question. Can you please repeat?
The question is a simple carburetor supply rich mixture during starting, idling. So both are confusing. So which one is perfect?
Is the assignment problem?
Yes, assignment problem. Just like my question is a simple carburetor supply rich mixture during which starting, idling.
Let me check if it is there in assignment 3.
One was best. Because recently you solve starting petrol engine require rich mixture.
I am not supposed to tell you the exact answer, but I can explain what it does it mean. So simple carburetor supplies rich mixture during starting, idling, cruising, or accelerating. So idling
Yes.
means when you don't, your load is 0. Okay, when your load is 0, you just need to keep your engine on running. Okay, without any load.
Yes, sir.
Okay. Accelerating, for example, you are going uphill. Okay, so at that time you are having more load, or you are accelerating on a road.
So
Okay,
confusion between starting and idling, not accelerating and cruising.
starting, you can say it is like cold starting. In that sense, you can think.
No, sir, just normal starting.
Normal starting means your engine, you just starting your engine, and whenever you're starting, it is starting from cold. Okay, and after few minutes it becomes hot, right?
Okay, sir.
Starting means you are starting your bike, you just turned on your switch. Okay, so starting means that, right? So most of the time when we say cold start, we means that initial temperatures are very very less, and to ignite the fuel when the temperatures are less, it is difficult, right? So we say it is cold start. Okay,
Okay, sir.
but during starting, temperatures are less, no matter how hot it is. Even during your summer, temperature will be how much? It will be like 40 or 50 degrees Celsius. So that is what starting should refer to in this question. Okay,
Yes, sir. Okay.
but anyways, so
15 is
question
to
number
1.
stoichiometric air fuel ratio of petrol is roughly. So you know what is stoichiometric air fuel ratio? Air fuel ratio
Actually,
means air fuel
Chemical
ratio.
required.
Yes,
Air
air fuel ratio means mass of air divided by mass of fuel. in the mixture.
Yes.
Okay, and stoichiometric means a chemically correct mixture, right? So what I mean by chemically correct is, for example, you have one carbon atom, and if you want to burn it, then you need two oxygen and you get CO2. So this equation is balanced. Okay, so this is an stoichiometric equation. So I have not written nitrogen and other things that are attached to the carbon atoms, but you can write them down as well. Okay, so this is stoichiometric. So stoichiometric means the exact amount of air that will be required to burn the fuel, right? In a chemically
Yes, sir.
correct.
Complete.
Mm. So for complete correct combustion in a chemically balanced equation. So for petrol, how much this is roughly the range?
Sir, for diesel,
Hello, hello.
yes, sir.
Okay. So how much?
Hello.
Uh-huh.
15:1 for
15 is to
petrol.
1.
For diesel, how
Okay.
much, sir?
Okay. For diesel, how much? Or for any other fuel, how much? For CNG, how much? So you have already given the answer that the chemical reaction should be balanced. For example, let us say the example of petrol itself. So for petrol, so petrol or diesel or anything, these are basically mixture of various compounds. Okay, so what happens? You have the crude oil and you refine the crude oil and you get petrol or diesel. But these diesels or petrol, they are basically mixture of many compounds. For example, in petrol, there are a lot of compounds, but the main compound or the reference fuel that you can, the reference compound that you can take for petrol, it is usually taken as C8 or octane, C8H18. Okay, for petrol. But this is not the only compound in the petrol. There are other compounds as well, and this is one of the compound. Okay, so let us take C8H18 and assume that this is the petrol. Okay, now you want to burn this C8H18. You have to write a chemically balanced reaction. So let us say you, for 1 mole of C8H18, you need a mole of air. A mole of air. Okay, so in 1 mole of air, how much nitrogen is there? Around 80%, right? And oxygen is around
20.
20%.
20.
20%, correct?
Yes.
So nitrogen is around 0.79% and oxygen is around 0.21. ठीक?
Yes, sir.
Now after combustion, what will you get? You will get CO2. So how many carbon atoms are on the left side? There are 8. On the right, there are 1. So just multiply by 8. Okay, so now carbon, it is balanced, right? You need to balance the hydrogen as well. So on the left hand side, you have 18 and here you will get H2O for complete combustion. Reality में ऐसा नहीं होगा, दुनिया भर की और चीजें बनेंगी. So 9 H2O. Okay, so hydrogen is also balanced, correct? Right?
Yes, sir.
Now you need to balance
Yes, sir.
oxygen. You need to balance oxygen. So on right hand side, how many oxygen atoms are there? 8 into 2, 16 plus 9. So how many are there?
25.
25 oxygen atoms, right? So 25 oxygen atoms on the right hand side, and on the left hand side, how much? A into 2 into 0.21, right? Correct?
Yes.
Yes, sir.
That should be equal to 25. So A will be equal to how much? A will be equal to 25 divided by 2 into 0.21, right? So this, so like this you will get A. Okay, and oxygen will be balanced. And what will be left? Only nitrogen will be left. So it will be 0.79 times A N2, right? So you just need to find the value of A. Let us find how much it comes. Let us check. Okay. So 25 divided by 0.21 into 2.
59.52.
59.52. Okay. So for 1 mole of octane, you need 59 mole of air. Okay. So what is the molar mass of this octane? I am doing a rough calculation. Let us take the molar mass of carbon to be 14, right? 14 or 12?
12.
12, right?
12.
12 into 8 plus 18. So this is the molar mass of octane. So how much it is?
114.
Hmm?
144. 114.
Okay. So for this much, this is the mass. Okay. And for air,
114.
114 किसका है? For air, 0.79 multiplied by नाइट्रोजन कितना होता है?
14. 14.
मतलब प्लस 0.21 into 2 into 16. So ये कितना है? $28. 28.84. Okay.
Yes, sir.
पहला कैलकुलेशन क्या 114 होगा.
114 ऐसा?
Yes, sir.
Okay. So for 1 mole of C8H18, you need how much? 59.5. Just take 59. Okay, 59. Okay, 52 mole of air. Okay, so 1 mole of C818 means 114 gram of CH18. You need 55.52 multiplied by 28.8 gram of air. Okay, so क्या निकालना है इसमें? Air fuel ratio. So air fuel ratio will be 59.52 into 28.8 divided by 114. So let us check this value. 59.52 into 28.8
15.36.
divided by 114. तो कितना आ रहा है? ये आ रहा है 15 के अराउंड. Okay.
Yes,
So this is how we calculate the air fuel ratio for any fuel. So for petrol, this is the reference fuel and the air fuel ratio is coming out to be 15. So 15:1. So C part is the correct. And you are asking about diesel, right? So for
Yes,
diesel,
sir.
it's also a mixture of many compounds. So for diesel, mostly we take C10. Okay. C10,
18 to 100.
C10 H22. Okay. For diesel. And for petrol, we have this. Okay.
Yes, sir.
So for diesel also now using the same way you can find the stoichiometric air fuel ratio. For
Yes,
any
sir.
fuel you can find. For CNG mostly we take CS4, right? So for any fuel you can find it like this. Okay.
Yes.
Is it
Sir,
clear?
1:1 in last option 1:1 there that is for which mass flow rate of air equal to mass flow rate of fuel.
Yes.
In which case it is possible?
In which case it is possible? So this means your fuel will be having very less calorific value, right? जितनी हवा जा रही है उतना ही आपका फ्यूल जा रहा है. तो 1 घंटे में अगर आपकी 1 किलो मतलब 1 घंटे में आपकी कुछ किलोग्राम हवा जा रही तो उतना ही किलोग्राम फ्यूल जाएगा. तो इतनी बड़ी टंकी तो नहीं लगेगी. So this is just a hypothetical situation.
Yes, sir.
Okay.
Okay, sir.
For example, if you are using 1 liter of petrol, then you will have to use 15 liter of petrol for the same thing, right?
Yes, sir.
That will be, there can be some fuels, but those fuels will be, you know, not very practical for our use, right?
Sir, is there any formula there for minimum air required to combust of fuel of 1 kg air by fuel stoichiometry is equal to 8 times of hydrogen plus 8 by 3 of carbon plus 1 time of sulfur minus oxygen into 100 by 23.
Can you please repeat?
Air by fuel stoichiometric is equal to 8 time of hydrogen H2 molecule plus 8 by 3 of carbon C plus 1 time of sulfur minus 1 time of oxygen O2 whole bracket 100 by 23.
Yes, actually, how to find a stoichiometric ratio, that we have already seen. How to find
by
equivalence? Yes. How to
by
find equivalence?
if
How
we
to,
put the value in this
no,
formula, can we get 15 is to 1?
you will not get that formula is most probably, whatever I understood, whatever you are saying, that is most probably for calorific value. That is for calorific value. Have you used the calorific value here? We have not used the calorific value, right?
Not used.
Right. Calorific value, when will you use calorific value? To calculate the thermal efficiency, right?
Yes, sir. M dot F into CV.
M dot F into CV, right? How
Heat
much work
supply.
output are you getting at the shaft? Brake thermal efficiency, if you want to calculate how much work. Yes.
Brake power by total power. Brake power
Yes.
by 2.20 divided by M dot F into calorific value.
Yes. So then you need the calorific value.
Yes,
And
sir.
what you call this formula? I forgot the name. I think Dulong formula. Let me check.
Dulong.
So Dulong formula is used for finding what? Calorific value, right?
If a question given, formula type given means we apply this formula.
Well, this formula is like a empirical relation, empirical formula. Okay. So using a lot of fuels and having the calorific values of those fuels. So this is a rough estimate. You will not get always the correct value. Okay.
Yes, sir.
So a rough estimate you can get, but if you think you will get correct value, it is not like that.
Sir, another doubt. Sometimes we use fuel by air by fuel. Equivalence ratio equal to fuel by air ratio. Actual by
No,
stoichiometric.
it is different. I will explain. Okay, let us discuss one by one. First question you asked about Dulong formula. Okay. So Dulong formula is about calorific value, right? And calorific value is about how much heat or thermal energy you are getting after burning 1 kilogram of fuel. Okay.
Yes.
When you burn any fuel, what is happening? There is some chemical reaction is taking place, right? And when the chemical reaction take place, some bonds are broken and some new bonds are formed. Okay. For example, you had the octane here. So this was an octane, normal octane. But this C10H18, sorry, C8H18, this can have various, arrangements. What do you call them? Isomers, right?
Isomers.
And depending on how what is the structure, how these carbon atoms or any other atoms, they are combined together, depending on the type of bond and the structure, the chemical reaction will be different, right? Are you getting what I mean?
Yes, sir.
If they are clustered together, then it will be difficult for them to break, right? For them to break. If they are like a chain, it will be easy for auto-ignition, right?
Yes, sir.
So the same fuel, which has the same chemical composition, but it has different structure. Okay, how different structure means how they are joined together, right? They can have different calorific values. But in your formula, your Dulong formula, it is only depending on the number of atoms, right? So can it be correct?
No.
So it can give a rough value, but exactly how much energy you will get after burning 1 kilogram of fuel, that depends on a lot of parameters. So what is the bond structure, how these atoms are joined together, right? if they are simple plane, I mean, they are normal chain or they are, ISO, right?
Yes, sir.
In chemistry, you have studied, right?
Oh, yeah. Yes, sir.
IUPAC names. So how they are combined, right?
Yes, sir.
Okay. So what was another question was there? I forgot.
If some place
Equivalence
equivalence
ratio, yes.
ratio,
Okay.
say ratio.
Equivalence ratio. So this, in the previous question, we have discussed the stoichiometric air fuel ratio, right? But you know that it is not always that you are running on stoichiometric ratio. Sometimes you are running on rich mixture and sometimes you are running on linear mixture, right? So this is stoichiometric, and whatever your actual air fuel ratio is, that will be different, right? Actual. Okay. So equivalence ratio, it is defined as actual fuel air ratio divided by stoichiometric fuel air ratio. Okay. If your let's just represent this by pi. Okay. So if your equivalence ratio is greater than 1, this means you are running on rich mixture. And if it is less than 1, this means lean.
Mix.
If it is equal to 1, then it's stoichiometric, right? So this is the definition of equivalence ratio. Here we are using fuel by air. If you want to use air by fuel, it will just get, reverse, reciprocal of this. Right?
Excess air ratio.
Yes, not excess air ratio, just call it air fuel ratio. Excess air ratio is something different. Okay, so basic things are same, just different names. Okay.
Okay, got it.
Okay. So we have one more question. A 4-cylinder, 4-stroke square engine. So you know a square engine?
Yes, sir. L equal to D. Length of stroke equal to diameter.
Bore is equal to stroke. Running at 40 revolution per second. I think this should not be correct. Okay, sorry, it is second. Fine.
RPS.
Yeah, RPS. Has a carburetor venturi with 3 mm throat. Okay. Assuming the bore to be 10 centimeter. Bore of engine is 10 centimeter. Volumetric efficiency of 75%. Density of air, it is 1.15 kilogram per meter cube, right? And coefficient of air flow is 0.75. And neglecting the compressibility, we have to find the suction at throat.
Means a pressure difference. Pressure difference.
Pressure difference, yes. Suction means pressure difference. So we have to find the pressure difference. And how do we find the pressure difference? It is simple. How do we find that?
Bernoulli's equation.
Can you use always use that Bernoulli equation?
No. Water whenever air is treated in compression, then only. If
Yes,
not,
yes, exactly.
flow energy.
Yes, if this term, it is given that you can assume that air is incompressible. Okay, you are neglecting the compressibility, so you can use. But if this thing was not given, then you'll have to use equation, energy equation, right? Steady flow equation. So, but this is the simple one, right? So you can simply use the Bernoulli equation. So you can write in terms of mass flow rate. It throat area. Do
you want me to use ChatGPT to?
Why this is?
I didn't.
Anyways, 2 rho A into delta PA. So this is fine. This comes from Bernoulli equation. Hello?
Yes, sir.
Mass flow rate is density times area times velocity, right?
Rho AB.
Right?
Yes, sir. We can replace the velocity term.
Replace the what term?
Velocity.
Yes, we can replace the velocity term. And there one more CD is there, right? So this is the same thing. Okay. So what we have to find?
Pressure difference.
Pressure difference. PA we need. Okay. And CD, I think what is, let us check what is given. Venturi has 3 mm this thing area. So
that area pi by 4 L square or L into B? Pi by 4 L square.
can you please repeat?
Area piston area or which area?
See, there are two different things. There are two different things. Bore is the piston area, but venturi means 3 mm is the diameter of venturi. Okay. Sorry, 3 centimeter is the different area of venturi.
Then venturi
Okay.
area.
So venturi is different. Venturi is related to carburetor, and your cylinder is different. Okay.
Yes. Then volumetric efficiency also given.
Volumetric volumetric efficiency is also given. So from the volumetric efficiency, what can you get? You can get the mass flow rate, right? Or the volume flow rate, right? And from the volume flow rate, you can get the mass flow rate. And when you get the mass flow rate, then you can use this equation, right? So let us do it one by one. So first of all, we will start with the engine. Okay. So for engine, what is given? Assuming the bore. Okay, bore and swept volume is same, right? Sorry, bore and stroke is same because it is square engine. So swept volume that will be equal to pi by 4 times area. Area, how much area is this? Bore is 10. So 10 centimeter into 10 to the power minus 2. So now it is in meter, right? This is squared. So this is area multiplied by the multiplied by stroke. So stroke will be same 10, right? So this thing 10 into 10 to the power minus 2. So now this thing will come into meters. So pi you take 3.14. So it will come out to be 0.00314 meter square. Okay.
7.85.
Now this is swept volume. Now if you need volume of air that is sucked per unit time or per unit second, that will be equal to number of cycles. How many cycles?
40.
40 divided by 2 because it is a 4-stroke engine, right? So 40 divided by 2, these are the number of cycles. In one cycle, how much area? 0.00314 meter per square. And volumetric efficiency, it is given to be 75%, right? 0.75. So now you will get the volume per unit time. So if you calculate this value, 20 into 0.00314 into 0.75, 0.047 meter cube per second. Okay. So mass flow rate, what will be the mass flow rate now? Just volume flow rate multiplied by the density, right? So 0.047 into density kitna? 1.15 kilogram per second. So
0.054.
So mass flow rate, it is coming out to be 0.054 meter cube, sorry, kilogram per second.
kg per second.
Okay.
Yes, sir.
So now you can use this equation. Mass flow rate will be what will
m dot a equal to cv into area into square root of c, that term.
mass flow rate will be equal to CD
cd
times area. Whenever I said CD, my phone understood as CD. No, it is not CD. Area. So A2 area is basically throat area into what? Velocity, right? And density, right?
Yes, sir.
Correct?
Yes.
Correct.
But coefficient of flow, it is given to be 0.75. So and if you use the Bernoulli equation as you are saying, then what it will be? It will be P1 plus V1 square by 2 will be equal to P2 plus V2 square by 2. So P1 minus P2 equal to V2 square minus V1 square by 2, right? So delta P is equal to one more approximation you can make, that since the throat area is very small, so V2 square, it is very greater than V1 square, right? So delta P will be approximately equal to V2 square by 2, right? So V2 you can take as delta P times 2 to the under root, right? Correct?
Yes, sir.
Rho is also there. Rho V square, right?
Rho V square.
Rho V square. So like this. Okay. So rho भी आ जाएगा यार. Okay. And since this thing is given, coefficient of airflow. So I think that rho is already included in the coefficient. Okay, so I don't think that you need to write it here. You can just remove from there. Okay. So only thing you need, mass flow rate is equal to CD times area into velocity. Okay. Hello.
Yes, sir.
And velocity we have find that it is equal to under root 2 delta P times rho. Okay. So delta P will be equal to m divided by CD into A2 squared divided by 1 by 2 rho, right? So you have all the values now. Just substitute these values. So mass value is 0.054. Divided by CD is 0.75. Area will be pi by 4 into इसका throat area कितना 3 centimeter. 3 into 10 to the power minus 2 squared. Okay. And this whole thing will also get squared into 1 into this is the density of air. Okay. If you calculate this value, you will get delta P.
4510.9. 4511.
Unit. SI unit. Because all the units are in SI unit, right?
Yes, sir.
So this is the delta P. So which delta P is this? Which delta P is this?
Suction.
So this delta P is so this is your venturi tube. So here it is delta P1 and here it is delta P2. So this delta P is basically P1 minus P2. But one more thing you should note here is that your fuel reservoir, right here, that is also open to atmospheric pressure, right?
Atmospheric pressure.
Yes. So pressure at 0.1 and here this is also P1. Okay. So we can in so this pressure and this pressure, they can be very close. Okay, they cannot be exactly same because air is flowing inside this pipe, so there will be some pressure difference, but you can get an idea that this difference will be somewhere related to this pressure. Okay, so sometimes in some questions it is given that let us say here it is pressure P3, so sometimes it is given that P1 minus P2 is some factor of, sorry, P3 minus P2 is some factor of P1 minus P2. In some question, you will get something like this, but you know how to solve. Now you have got P1 minus P2, you just multiply by this factor X. Okay, in this question, we don't need to do that, but for some other questions that you can encounter, you can solve like this. Okay.
X equal to 1. No?
But anyways, you have got this value, right? Delta P or the suction pressure, it is 0.0411 bar. Okay. Okay. Anyways, so I think we are running out of time. We will just read this question. A simple jet carburetor is required to supply 5 kilogram of air, 5 and 0.5 kilogram of fuel per minute. The fuel 0.5 kilogram fuel per minute. Okay, so calorific value will be very small. I don't know which engine this. Anyways, the fuel specific gravity is 0.75. So this is density. Okay, specific gravity means density. The air is initially at 1 bar at 300 Kelvin. Calculate the throat diameter of choke for flow velocity of 100 meter per second. Velocity coefficient is 0.8 if the pressure drop across the fuel metering orifice is 0.8 of that of choke. Okay, so that's what I was talking about. In the previous question, you have found out the pressure drop across the choke. Okay, now the pressure drop across the fuel metering orifice is basically P3 minus P1. Okay, P3 minus P1. Sorry, P3 minus P2. Okay, so P3 minus P2, it is 80% of P1 minus P2. Okay, so this is what I meant in the previous question. Calculate the orifice diameter assuming these values. Discharge flow coefficient, it is given. Okay, so CD is 0.6 and gamma is 1.4. Okay, so you just note down this question or you can take the screenshot or whatever.
Yes, sir.
You can try to solve it yourself. If you have any doubt, then we will solve it in the next question.
Yes.
And your doubt, one more doubt. Okay.
Hybrid
So,
electric. Sir, in a hybrid electric modern vehicles, gasoline, diesel, and all are used. Petrol, diesel, gasoline.
in what?
Hybrid electric vehicle.
Hybrid electric vehicle, it is running on combustion engine and the battery as well. So engine can be of, any engine it can be. Hybrid means combustion plus battery. So it can be diesel or petrol.
Gasoline.
But along gasoline and petrol are same thing.
Acha, and natural air, CNG type.
Yes, it can be any engine. It can be CNG or any engine.
Okay, sir.
But most of the time CNG, I mean, the gasoline and petrol are same thing. Okay, so you should not confuse the gasoline with the gas. Okay, yes, you call gasoline as gas in in America and some other countries. If you are going to their petrol pump, they will call it gas. Okay, or gasoline. We call it petrol.
Hybrid electric vehicle run with natural gas also, na? Modern hybrid vehicle.
See, technically, hybrid means combustion engine and a motor, electric motor. Electric motor will run with the battery and the engine that can run on any fuel. Okay, that engine can be a diesel engine, that engine can be a petrol engine, or that engine can be any combustion engine. Okay.
Yes, sir.
So hybrid vehicles also of many types. So some vehicles or some hybrid vehicles, you need to charge your battery from some external source. Okay. like the electric vehicles. And in some hybrid vehicles, your battery is charged from the engine. Okay, it takes power from engine and it gets charged. So depending on so there is some map. Okay, so map means basically at this RPM, at this load, if you run on battery, then it will be better. And at that particular load and that particular RPM, if you run on engine, that will be better. So there is some optimization. Okay,
Yes, sir.
and other things as well. For example, when you are applying brakes, so how the brakes work? Brake convert your energy, kinetic energy, into heat. But in electric vehicles or in hybrid vehicles, they are using regenerative braking. Okay, so kinetic energy, that is, stored as, power in the battery. Okay, so a lot of technology is used. Okay,
Sir, which is
and
more move faster, hybrid electric or normal IC engine?
it is not more important is not faster. Okay, faster means you can use the gearbox and you can run any vehicle at faster speed. Okay, you just use
Yes,
the
sir.
gearbox. Okay, so fast speed depends on how fast you are rotating, but more important is how effective it is. Okay, how less pollution it is making.
Specific fuel consumption is less.
Specific fuel consumption is less. So there are a lot of analysis. For example, one analysis called life cycle analysis.
Uh,
So in one life cycle analysis, what they do is they do a study from cradle to grave. So cradle means when, for example, you need to make one vehicle, let us say one combustion engine. Okay, so what are you doing? You are digging the earth, you are taking out the iron ore, you are melting the iron ore, you are making the engine. Then to run the engine, you are putting some fuel, and that fuel comes from some other countries using some transportation. And then it needs to be reached to be your petrol pump, and you are going to petrol pump filling the fuel. Then you are running and you are burning some fuel. Okay, so after some years, your life of your engine will be completed. Then you need to recycle this engine, right? You will send this engine to scrape, and that scrape person again, this will melt this engine. So in the whole life, uh, how much kilogram of carbon dioxide has been emitted? So that is called life cycle analysis. So this life cycle analysis can be done for any types of engine or anything. Okay, so uh, for your electric vehicle, you can do your LCA. For your hybrid vehicle, you can do LCA. For combustion engines, you can do LCA, and see which engine is making less pollution. So this is one scenario. Another thing is called total cost of ownership. Okay, how much it is affecting your pocket. Okay, so there are a lot of analysis. So which parameter is more important to you, pollution or money or something else? Okay, diesel
yes.
engines, the electric engines also make pollution. So they have the green number plate. That does not mean that they will not make any pollution. For example, if you want to make the battery, so for battery you need to take out the lithium, and to process the lithium you need a lot of water. And when they complete their life, we don't know how to recycle the battery. Okay, the recycling of battery is very very challenging, and they are very heavy. So lot of things are there. Anyways, you just note down this question. More
Yes, sir.
discussion at some
Noted.
other day, but uh,
Sir,
there are
in
few. Mhm.
for this V Ghanshyam is good for solving numerical.
Yes, in veganism you can find some good numericals. These numericals are also from the veganism only.
Achha, okay. For IC engine and gas turbine.
Veganism book is there, no, for IC engine. So you can
Gas
refer that.
turbine. Gas turbine also same writer.
I'm not sure. No, I need to check.
Okay.
Many good books are there on engines. Like what we use is this book.
JP
Uh,
Haywood.
JP Haywood, yes, you might have seen this one, right?
JP Haywood.
Yes, this is Haywood.
This is Bible.
You can say yes. It is a very good book.
Okay, sir. Okay, sir. Fine.
Okay. There are some other problems. For example, that assignment problem that I will try to solve in next session maybe. But data is sufficient. You can solve that problem. And
Sir, for maximum and minimum that pressure term, we will solve next section.
okay, we will discuss that problem. Okay, minimum and maximum. Yes, that problem. Assignment 2, question 8, right?
Uh,
Okay, we will sort in the next session, and you try to solve this problem by yourself. If you
Yes,
have any
sir.
problem, we will solve, and answer for this question I have already given.
Yes, sir. Please
Okay.
upload it in the video so that we
Sure, sure, sure. Okay. Thank you for joining.
Thank you,
Okay.
sir.
Good night.
Thank you,
Take
sir.
care.
Good night.